Hi, we continue chapter 6 and we will define the power functions. Let alpha be a number in R, a real number. A power function of exponent alpha is the mapping denoted f alpha defined by. So f alpha is going from 0 to plus infinity into R, and to each x it corresponds f alpha of x being equal to x to the power alpha. And you might ask yourself why we are defining a power function even though you know the functions like x2, x to the power half, x to the power 3 over 2, x power 5, you know all these functions. But the thing is that in here we are defining these functions for alpha belongs to R. So alpha might be radical 2, for example. Okay, so these functions, you don't know them. So when alpha belongs to R, it's another way of defining the function. So we define the x to the power alpha as being e alpha ln of x. So let's say x to the power radical 2 is equal to e radical 2 ln of x. So if you see something like this, it means it's this function, which makes sense because it's an extension of the definition we already know for alpha integer or alpha rational. Let's say, for example, alpha is equal to 2. So your function will be x to the power 2, which according to this definition is equal to e to the power 2 ln of x, which is e ln of x squared, which is equal to x squared. So it's the same thing. I mean, if you define it like define the function like this or like this, it's the same thing. When alpha is an integer, even when alpha is a rational, and when alpha is an irrational number, it's an extension of the former definition. Now, since this function is not defined for x equals to 0, it contains ln of x, so it's only defined when x is greater strictly than 0. So we are extending the definition of the power functions we already know for rational powers to functions when the powers are irrational, but only when x is greater strictly than 0. So now, since it's not defined at 0, we will calculate the limit when the function goes to 0. So the limit of f alpha of x when x tends to 0 is equal to the limit of e alpha ln x. So this tends to minus infinity, then e minus infinity will be equal to 0. This, of course, if alpha is positive. Then for alpha positive, we will extend the functions to the point 0 by the value f alpha of 0 equals to 0. Of course, these functions are c infinity on 0 plus infinity, and we have the derivative f prime alpha of x being equal to alpha over x e alpha ln of x, which is alpha x to the power alpha minus 1, which is very nice because it also agrees with the derivative of the power functions when alpha is an integer or a rational. Okay, and if we calculate also the second derivative, it will be also alpha minus 1 x alpha minus 2. So it also agrees with already what we know about the derivative of x to the power 2, x to the power 3, and all the power functions when alpha is rational. So the table of variations of f alpha will be given for two cases, when alpha is negative and alpha is positive. If alpha is negative, this derivative in here will be negative, so the function is decreasing, and if alpha is positive, then the derivative will be positive and the function is increasing. And we have the limits. When x tends to 0, it goes to 0 when alpha is positive, and it goes to plus infinity in the case when alpha is negative. And then we can draw these functions. If alpha equals to 1, it's the equation y equal x. If alpha is negative, then it's like let's say 1 over x, so it's the hyperbola. If alpha is equal to 0, then the function is y equals to 1 in this case. And then if alpha is greater than 1, it's the example of the function x2, x3, etc. It has this kind of shapes, so it can be like this or like this or whatever. It has the same shape. It's convex and it's going towards plus infinity parallel to the y-axis. And if alpha is between 0 and 1, it's the case, for example, of radical x, then it goes like this. It's parallel to the x-axis. So we finished with the power functions, and we'll define now the hyperbolic functions. Now, be careful, hyperbolic functions are not the hyperbole that you already know. It's something different. Let me say something first. You may know or not that any function f can be written as a sum of an even function and an odd function. If a function f, any function f, we write it like f of x plus f of minus x over 2 plus f of x minus f of minus x over 2, then it's the sum of two functions. This is the first one, let's call it h of x, and this is the second one, which is g of x. And we can notice that h of x is even because h of minus x is equal to h of x, because you can replace x by minus x, you'll have the same function. And also g of x, we notice that it's odd because g of minus x, if you replace x by minus x, you will have minus g of x. So it's a way of writing f as a sum of two functions, an even function and an odd function. Now if we apply this to the exponential ex, it will be written as ex plus e minus x over 2 plus ex minus e minus x over 2. Of course this is equal to ex, because if we add these two, e minus x would be cancelled with e minus x, and then you will have ex at the end. So if you write ex as this sum, you will have the sum of two functions. The first one is even, the second one is odd. And these two functions will be the functions that I'm considering in this paragraph. So this one will be called the hyperbolic cosine, denoted ch hyperbolic cosine x, and the second one will be the hyperbolic sine, which will be denoted sh of x. And I will be studying these two functions in this paragraph. So first, the hyperbolic sine function is the mapping defined from R into R. The domain of definition is R because the exponentials in here can take any x in R. So the function will be defined as the mapping that to x it corresponds sh of x, which is equal to ex minus e minus x over 2. And the hyperbolic cosine function is the mapping that corresponds to any x, ex plus e minus x over 2, and it's denoted chx. Now we will study these two functions. So since sh is an odd function, the hyperbolic sine, then we can make the study only on 0 plus infinity. And since also it's a c infinity function, then we will differentiate it. We calculate the derivative, the first one that we need right now, and the derivative of sh x is equal to the derivative of ex, which is ex, minus e minus x, so it's minus e minus x, which is plus e minus x over 2, so it's equal to chx. And also when we will calculate later now the derivative of chx, it will be equal to shx, which is very similar to the behavior of cosine and sine, the circular functions. That's why we are calling these functions, if you want, cosine and sine, because they have similar properties as the cosine and sine, but they are not the circular functions. So they are not functions having values between -1 and 1 and etc., which is the case of the circular functions, but they have similar relations. That's why we can call them cosine and sine, or we are calling them cosine and sine. And since chx is positive because it's equal to ex plus e minus x over 2, so it's always positive, then the derivative of sh is positive, and then sh is increasing on 0 plus infinity because we are doing the study on 0 plus infinity. And also we know that sh of 0 is equal to 0 by replacing x by 0, and we know also that the limit of sh when x tends to plus infinity is equal to plus infinity, because ex minus e minus x over 2, this term goes to plus infinity, this term will go to 0, and then overall it will go to plus infinity. So we have all this, and we can draw the table of variations that says that for x between 0 and plus infinity, sh prime is positive, the function is increasing from 0 to plus infinity. And since the value of the derivative at 0 it's equal to e0 plus e0, so it's 2 over 2 equals to 1, then the graph of sh has y equal x as tangent at the point 0, 0. Let's study now the function ch. The derivative of chx is equal to ex minus e minus x over 2, so it's shx, which is positive for all x between 0 and plus infinity. So we also do the study on 0 plus infinity because ch is even, and then ch is increasing, and by symmetry we can deduce that it's decreasing on minus infinity 0 because it will be symmetric with respect to the y-axis. Then it will have a minimum where the function or where the derivative will be equal to 0, which is the point equals to 0, when x equals to 0. And the image of this point is 1, so it has a minimum at 0, 1. Now drawing the table of variations of ch, it has the derivative positive, so it's increasing from 1 to plus infinity because the limit at plus infinity is equal to plus infinity. So if we draw these two functions, they will have this shape, sh going from 0 to plus infinity. It has a direction parallel to the y-axis, and it's symmetric with respect to the origin because it's odd, and then ch is increasing from 1 to plus infinity, and it's also symmetric with respect to the y-axis. And I drew in here an additional function which is ex over 2, which is a function that goes from 0 in here and goes to plus infinity between the two other functions. So these two functions are, these three functions even, are asymptote to each other at plus infinity. We can now prove the following properties for these functions. First, it's obvious that chx plus shx is equal to ex because the e minus x will cancel. This is what I started with. And also the difference between ch and sh is equal to e minus x. Now also we can prove that if we take ex plus e minus x over 2, which is chx to the power 2, minus ex minus e minus x to the power 2 over 2, if you do the calculation you will obtain 1. So we have the following formula, which is ch squared x minus sh squared x equals to 1. And we can also prove, using also the exponentials, that cha plus b is cha chb plus sha shb, and cha minus b is equal to cha chb minus sha shb. In fact, it's very similar to the formulas we obtain with cosine and sine, but be careful, it's not always the same signs in here. It might be different, so it's not the same formulas. But it's very similar also for the sh a plus b and a minus b. And for the ch2a, it's equal to 1 plus sh squared 2a, which is also similar to cosine and sine. And it's equal as well to 2ch squared a minus 1 due to this formula in here. And then sh2a is equal to 2 sha chb. Now, these formulas allow us or push us to call these functions as cosine and sine because they show similar formulas as in cosine and sine. And this formula here pushed us to also call them hyperbolic functions because it's the equation of a hyperbole when chx is equal to big X if you want, and shx equals to big Y. Now, since shx is an increasing function, strictly increasing and differentiable, then it has an inverse function. And since chx is strictly increasing from 0 to plus infinity, then it has also an inverse function on this domain, and we will define now these inverse functions. These inverse functions, we will call them arg chx and arg shx. So first, the function arg sh, since sh is continuous, strictly increasing, and it goes from r into r, then it has an inverse function which is continuous, strictly increasing as well, which will be denoted arg sh, and it's defined by arg sh going from r into r. And the graph of arg sh, of course, is symmetric to sh with respect to y equal x, and we can write that if y is equal to arg shx, it means that x is equal to shy. Also, arg sh is odd as sh and differentiable, and the derivative of arg shx is 1 over the derivative of sh at the point which is a pre-image of x, which is arg shx. So it's 1 over the derivative of sh is ch at this point, and then ch of arg shx, it's equal to square root of 1 plus sh of arg shx, and sh of arg shx is equal to x. So it's 1 over square root of 1 plus x2. And if we draw the table of variations, of course it's an increasing function, and using the symmetry it goes from 0 to plus infinity. Now we can express arg sh as function of a logarithm. How we can do this? Since for all xy in R2, if y is equal to arg shx, it means that x is equal to shy, then x is equal to 1 over 2 ey minus e minus y, right? Which is equivalent to e 2y minus 2x ey minus 1 equals to 0. And we obtain this by replacing e minus y by 1 over ey and doing the common denominator. So why did we wrote this? Because we want to transform the way of writing arg sh into an exponential or a logarithmic form, since shx itself, it's an exponential expression. And this type of calculations you should be able to do it as an exercise, so you have to study how we are doing it exactly and then memorize the result. So if we call ey in here, we call it like big T, then we have a second degree equation in T which we will solve, and it will have two solutions, x minus square root of 1 plus x2 and x plus square root of 1 plus x2. But since square root of 1 plus x2 is greater than x, so this t1 in here is negative, then it's not the good choice, because t is equal to ey and ey is always positive. So t2 equals to x plus square root of 1 plus x2 is the good choice. Then we will say that ey will be written as this t2, and then y is equal to ln of what's in here, so this is the y, which is arg shx. So we are able to write arg shx as a logarithm because sh itself is an exponential form, so calculating the inverse function should be, or should give, something like a logarithmic form. Now going to the arg ch function, it goes from 0 plus infinity, or we take the restriction from 0 plus infinity to 1 plus infinity, and this restriction is continuous, strictly increasing. Then it has an inverse function, and that we will denote arg ch, that goes from 1 plus infinity into 0 plus infinity. And if y is equal to arg chx, then x is equal to chy, and if we calculate the derivative of with the same formula, we have the derivative of arg ch prime, it's 1 over ch prime of arg chx, which is the pre-image of x. It's equal to 1 over sh, because it's the derivative of ch, at arg chx, but sh of something, it's equal to square root of ch of this something, so ch of arg chx minus squared, of course, minus 1, and ch of arg chx, it's equal to x. So the derivative is equal to 1 over square root of x2 minus 1. So the table of variations of arg ch will be showing that the function is increasing, the derivative is positive, and since the derivative of ch as 0 is equal to 0, because it has the horizontal line as tangent, then the derivative of arg ch at 0 will be equal to plus infinity. We have a vertical tangent. Also, arg ch can be written as a logarithmic form, because since ch is an exponential expression, then arg ch, it's logical to have it as a logarithmic form. We do the same thing that we did with the sh, with the sh, sorry. So we write y equal arc chx, then x is equal to chy. We write it in the exponential form, and then we form the second degree formula by replacing e minus y by 1 over ey and calculating the common denominator. Then we have a second degree equation where t is equal to ey, and calculating the solutions we have t1 being equal to x minus radical x2 minus 1 and t2 equal to x plus radical x2 minus 1. Now let's check if x minus radical x2 minus 1 is less than 1. So if this is true, then we should have radical x2 minus 1 greater than x minus 1. So since this is positive because x is greater than 1, then we square both of them. Then we should have x2 minus 1 greater than x minus 1 squared. So this is true if this is true, but this is true in here if x2 minus 1 is greater than x2 minus 2x plus 1, which means that minus 2x plus 2 is negative, and this is true because x is greater than 1. So this is true in here, and then t1 is less or equal than 1. So t1 is not acceptable because t should be equal to ey, which is greater than 1. Then it's the t2 that we are taking because it can have values greater than 1. It's also always greater than 1. Then ey is equal to x plus square root of x2 minus 1, which means that arg chx is equal to ln of x plus square root of x2 minus 1. So this is the logarithmic form that you should know about arg chx. Now if we draw these functions, the chx goes from 0, 1 to plus infinity in here. So if we draw the symmetric of this function, it will be this one, the arg chx, that goes from the point 1, 0 and to plus infinity parallel to the x-axis. So it's symmetric to chx. And if we look at, of course it's symmetric to the part of chx on 0 plus infinity. And if we take shx, the whole function, because it's always increasing, then arg shx will be this red function in here, symmetric to sh with respect to y equal x. We continue now with the hyperbolic functions, and we'll define the hyperbolic tangent, which is, maybe you guessed it, it's shx over chx. So it's ex minus e minus x over 2 over ex plus e minus x over 2. So we remove the over 2's, and then it's equal to ex minus 1 over ex plus 1 over ex, and doing the common denominator and then removing this denominator, simplifying it, we'll have e to x minus 1 over e to x plus 1. And then the hyperbolic cotangent function, which is chx over shx, which can read also e to x plus 1 over e to x minus 1. Since chx is even and shx is odd, then both these functions are odd functions, and they are c infinity, and they are defined on R. I mean, the tangent is defined in R, but the cotangent is defined in R plus R star, because you cannot have shx equals to 0 in the denominator. And then if you calculate the derivatives, th prime is equal to the derivative of sh, so it's ch times chx, minus the derivative of the denominator, which is shx times the numerator shx, over chx squared. So this is equal to 1. So the derivative is 1 over ch squared of x. It's also equal to 1 minus th squared, because 1 minus th squared is 1 minus sh squared x over ch squared x, which is equal to ch squared x minus sh squared x over ch squared x, and this is equal to 1. Okay, and then if you calculate the derivative of cotangent hyperbolic cotangent x, it's equal to minus 1 over sh squared x, which is 1 minus coth squared x. So we can do the same calculation as for the th in here. And then the limits of these two functions, at plus infinity th will go to 1, because if you take the exponential form, it will be e2x plus 1 over e2x minus 1. And if you take e2x as a common factor, so it will be in here e2x times 1 plus 1 over e2x over e2x times 1 minus 1 over e2x, and this is simplified, and then this goes to 0, this goes to 0, and the limit is equal to 1. So the limit of th is equal to 1, and doing the same thing, we prove that the limit of coth is equal to 1 as well at plus infinity. And the table of variations, the tables of th and coth will be as follows. th is increasing from 0 to 1 with a slope of the tangent equals to 1 at 0, and coth is decreasing from plus infinity to 1. So we have the point 0, 0 on the function th in here, and then we have an asymptote y equal 1, and since th is odd, then the symmetric part with respect to O will have an asymptote y equal to minus 1, and for coth we have also an asymptote equals to 1, and for the other symmetric part we have also an asymptote equals to minus 1. And in this case also we have another asymptote, which is x equals to 0, because when x goes to 0, coth goes to plus infinity. And if we draw the functions, we can see that you have this asymptote and this asymptote in here, and the function thx, it goes like this, and coth is asymptotic to x equals 0, and then it goes asymptote to y equal 1, and the symmetric part is in here. Now, these two hyperbolic functions, the th and the coth, they both are monotonic functions. th is always increasing and coth is decreasing. Then we will define inverse functions for these functions. First, we define the arcth, which is the inverse function of th. Well, the mapping th going from r into minus 1, 1 is continuous and strictly increasing. Then it has an inverse function, continuous, strictly increasing as well, and defined by arcth going from minus 1, 1 into r. So if y is equal to rthx, then x is equal to thy, and the graph of rth, of course, it's symmetric to the graph of th with respect to y equal x, and the derivative of rth, it's 1 over the derivative of th at the point rthx, which is 1 over minus th squared, which is the derivative of th, of arg thx, and this is equal to 1 over 1 plus x squared. So this is the derivative of arg th. So, and it's a c infinity function, of course, on minus 1, 1, and it's an increasing function, and since the derivative of th at 0 is equal to 1, then the derivative of rth at 0 is equal to 1 as well. And we can draw this function as being the symmetric to th with respect to y equal x, which will give the following. So this is th in here, then rth will be like this, and it will have the two asymptotes, x equal minus 1 and x equal 1. Now we can also, as we did for the arc-sh and arc-ch, we can also find a logarithmic expression for arc-th, doing the same procedure we did for ch and sh. So writing that y is equal to arc-th(x), of course, since y is equal to arc-th something, it's between minus 1 and 1. And then x will be equal then to thy. We transform it to the exponential form, and we calculate it as a second degree equation or so. So it's x times e to y plus 1 equals e to y minus 1, which will give that e to y is equal to 1 plus x over 1 plus minus x. So we need to calculate the y, but here the second degree equation is only with one term e to y. Then we can immediately deduce that y is equal to half ln of 1 plus x over 1 minus x, which is the logarithmic expression of rth when x is between minus 1 and 1. Now looking to coth, it's a decreasing function going from minus infinity 0, 0 plus infinity into minus infinity minus 1 union 1 plus infinity. So it has an inverse function, continuous strictly decreasing as well, but going from minus infinity minus 1 union 1 plus infinity into minus infinity 0 union 0 plus infinity. And we have for all x in minus infinity minus 1 union 1 plus infinity, for all y in r star, which is the range of r coth, sorry, we have y being equal to r coth x. It means that x is equal to coth y. And calculating also the derivative of the function r coth, it's equal to 1 over coth prime r coth x. So doing the same thing we did for the th, it will be 1 over 1 minus x2. And r coth will be also odd because coth is odd, and will be also c infinity because coth is c infinity on its domain. Then the table of variations will be given like this. The function is decreasing from plus infinity into 0. As we did for the thx, we will write a logarithmic expression of arg coth. So for all x in minus infinity minus 1, 1 plus infinity, y in r star, if y is equal to r coth x, then x is equal to coth hy, and we do very similar calculation as for the th, and we will obtain that r coth x can be written as half ln of x plus 1 over x minus 1. Of course, this is true when x is between minus infinity minus 1 and 1 plus infinity. And if you go to the graph, we see in blue in here the coth x, and in red in here the r coth x, which is symmetric to coth with respect to the yellow line y equal x. And also on the negative side of the graph, in blue we have the coth, and in red the r coth which is symmetric to coth with respect to the yellow line.